In this video for section 13.8, we'll be doing some examples of finding the relative extrema by using the second partials test. Here we have a function f of xy equals negative x squared minus y squared plus 4x plus 8y minus 11. What we want to do is find the critical points. The critical points are where the partial derivative with respect to x, where f sub x of xy is equal to 0, and the partial derivative with respect to y is also equal to 0 at the same time. So let's go ahead and find the partial derivative of this with respect to x. We treat x as a variable and treat y as a constant. We get that partial derivative is negative 2x plus 4. And we're going to find the partial derivative with respect to y. Treat y as a variable and x as a constant. And that partial derivative is negative 2y plus 8. We're going to set them both equal to 0. And by solving these simultaneously, negative 2x plus 4 equals 0, that happens when x is equal to 2. And you can subtract 4 from both sides and then divide by negative 2 to solve for x. If you solve this one for y, by subtracting 8 and dividing by 2, you get y is equal to 4. So this has a critical point at point 2, 4. To use the second partials test, we need those higher order partial derivatives. The partial derivative with respect to x and x again, like your second derivative, we take the result of the first derivative and take the derivative of that with respect to x, and that is negative 2. We're going to take the partial derivative with respect to y and y again. That's your second partials with respect to y. Looking at the partial with respect to y, take the derivative of this with respect to y again, and you find that that is negative 2. And then we're going to find that mixed partial derivative xy. And that's where you take the partial with respect to x, and then the result of this, you're going to take the derivative with respect to y, and you get 0. Use these values in your d, where d is that determinant. It's your partial derivative with respect to x evaluated at ab times your partial derivative with respect to y and y again evaluated at ab minus that mixed partial evaluated at that critical point, that quantity squared. Okay, and this, the critical point 2, 4, that's going to be your AB. Now in this example, there's no place to plug in A and B into those higher order partial derivatives. In this case, they're constant. But we can still find the value of this D, because for any AB, for any point, the second partial with respect to x is negative 2. For any point that you can plug in here, the second partial with respect to y is negative 2, minus what you get when you evaluate this mixed partial at any point is going to be 0. And then when we simplify that, we get this d is equal to a positive 4. Now, referring back to the second partials test, if d is greater than 0, and fxx is, in this case, it's less than 0, then we have a relative max. The relative max occurs at the points where x is 2 and y is 4. Now we need to plug that x and y back into the original function to find our z, which is 9. That's your relative maximum. Again, when the d is greater than 0 and the second partials with respect to x is less than 0, think of this as being concave down. Second derivative is negative. Concave down, then you have a relative max. And again, this is the second partials test at theorem 13.7, which is on your formula sheet. Again, we found the critical points, we evaluated the d, we found that d was greater than 0 and the fxx was less than 0, so that satisfies the second requirement here, that we have a relative maxima. Here's another example of finding the relative extrema for f of xy equals x squared plus 6xy plus 10y squared minus 4y plus 4. Go ahead and use the second partials test to determine if this has a relative max, a min, or a saddle point. Pause the video, work on this on your own, and then come back and check your work. Alright, to find the critical points, we're going to take the partial derivative with respect to x. Okay, you're going to set that equal to 0. Now the partial derivative with respect to x, you treat x as a variable and y as a constant. You get 2x plus 6y, that, and then the partial derivative with respect to y, you treat y as a variable and treat x as a constant, and you're going to get 6x plus 20y minus 4. We're going to set them both equal to 0 to find the critical points. Now you can find this using the substitution method, the elimination method, the graphing method, but I'd like to show you again how we can use the reduced row echelon form of a matrix to determine the solution. It does need to be in the form of ax plus by equals c and dx plus by equals f, so that we can build this matrix with just the numbers a, b, c, d, e, f, and then we're going to reduce row echelon form that matrix. So what we can do is to write this 6x plus 20y minus 4 equals 0. Just add the 4 to both sides so that you can write this in the form of 2x plus 6y equals 0 and 6x plus 20y is equal to 4. So our matrix is going to be the coefficients 2, 6, 0, 6, 20, and 4. And then we're going to use our calculators command to reduce row echelon form that. Okay, to build the matrix on the graphing calculator, we're going to press second, and then the matrix menu. We need to edit the matrix first. The size of the matrix is a 2 by 3 matrix. And the numbers are that we enter are the numbers from, pressing enter after each time. Okay, so we've entered the matrix, edited the values of the matrix A. Now we're going to quit this screen, second quit, go back to the matrix menu, and this time we're going to go to the math command and scroll down until we find the command for RREF. That's reduce row echelon form. Okay, in this case it's letter B. I'm going to press enter. And I need to have it reduce the matrix that we just created. So we go back to the matrix menu and just select the name of the matrix that you edited, and then you press enter. So by reducing this, we get the matrix 1, 0, negative 6, and 0, 1, 2. So that matrix was 1, 0, negative 6, and 0, 1, 2. So our solution to this system of equations is simply the values over here. X is equal to negative 6 and y is equal to 2. All right, so that's our critical point. Our critical point here is negative 6, comma 2. Now we need to find the higher order partial derivatives. We want to find fxx. Take a look at the first partial derivative with respect to x to get 2. You want to find fyy. The partial derivative with respect to y and y again is 20. And then that mixed partial derivative fxy is equal to, take the partial derivative of this with respect to y to get 6. Now d is our determinant. D is the partial derivative with respect to x evaluated at that critical point. Again, we don't have a place to plug in that critical point because those values are constant in this equation. The second partial with respect to y minus that mixed partial squared. So our value here for D is going to be 2 times 20 minus 6 squared, and that is going to equal 40 minus 36, which is equal to 4. Now, since our D is greater than 0 and our fxx, the second partial with respect to x, is also greater than 0, we can say that we have a relative minimum. And the point in space where there is the relative minimum, the x is negative 6, the y is 2, then if you plug these both into the original and simplify, you get 0. So our relative minimum of this surface is the point in space, negative 6 to 0.